So the work I'm presenting today is based on a project that we did from TU Kaiserslautern together with Bosch. So it's a collaboration with Nijso. And we are interested in general in edge joints and optimization for residential heating appliances. And in this particular talk, I will be talking about the optimization of the Venturi mixer. You can see in the right, well, this is positioned in the heating unit. Well, this is not right. No. Here, right here. And you will later see the geometry in detail. And what we are mainly interested in is that this mixer is concerned with mixing the fuel, in our case methane, and air before it enters the burner region, and then it significantly impacts the performance of the mixer, of the whole heating unit. And next to that, we are also interested in looking at the pressure drop in the system, because this makes a part of the pressure drop, and especially also looking at the mixing quality, so not only achieving a certain fuel to air ratio, but we want to have, for example, some homogeneity in the mixing. So we are considering different parts of this mixer for shape optimization. And what makes this case also interesting is that we don't want to optimize for a single operating condition, but we have multiple operating conditions. So this leads to a multi-point optimization. So what I will first be presenting the test case, and then I will go into detail with the multi-point optimization, and I will show some numerical results and also some comparison to measurements. So what makes this the multi-point problem? You see on the right, we plot the CO2 percentage, so that's what's usually measured. It's like not the fuel to air ratio, but the CO2 percentage that you can obtain from the fuel to air ratio over different powers. And you see that this varies over powers, especially for lower powers. We have a lower CO2 percentage. And you see this for the measurements and the simulation right here. And what we want to achieve is an ideal curve that is indicated here in purple with the thick line. So the objective would be to minimize the distance to this ideal curve. So to look a bit more into detail on the geometry, so this is a 3D cut through 3D geometry. And what you see here is the air injection part, so the air inlet right here. And here's where the gas enters. And then what we also have, so it entered through here, to adjust this is a needle that can be adjusted right here. And for our simulations, this needle position will be fixed. And furthermore, what makes the problem also more efficient is that we can solve this using a 2D axisymmetric slice of this geometry. So the simulation is incompressible runs plus an SST turbulence model. And for mixing, we are using cold mixing, so mixing from a lookup table for the transport of methane. And this comes from the feature flamelet branch, which is a branch in SU2 that is concerned with passive scale-up transport. So that's what we started off with. And then some flamelet, and we are using for this flamelet the cold mixing with lookup tables. And yeah, that's still a feature branch, but it's yeah, at the moment it's prepared for merging it into development. So yeah, and this branch also contains like the implementations for the optimization. So the objective functions that we need, for example, the fuel to air ratio and the mixing point. Okay, and here you see the convergence of the primary and edge joint. So we set this up alongside and with the edge joint solver, and this is validated against finite differences and also forward AE. And you see this converges quite nicely. alongside with the primary solver. So to use it now in optimization, first of all, we have to think about the different setting up these different operating conditions, and this is done using boundary conditions. We set a fixed pressure at the inlet, so at the gas and the air inlet, but then we vary the target mass flow at the outlet to reproduce the different power cases. So we will have a look at 3 different power cases, so low power, medium power, and high power, by setting different target mass flows. And on the bottom, you see like the mesh resolution and then the FFD box, how it's placed to alter then the shape of the Venturi for optimization. The objective function is then composed of the 3 different cases. So it's a sum over all contributions, where I look at the deviation of the fuel to air ratio at the operating power from a target fuel to air ratio, which is in our case set to the same target value for all powers, and this is squared. What's worth mentioning is that one might optionally be interested in adding a regularization term if the problem is somehow imposed, but in our case it was not necessary. But you can find this like targets, setting the target function and regularizing in my fork of FADO. So I'm using FADO for the framework of the optimization because it's quite convenient to set up the different cases for the multi-point setup. Okay, and here you see the on the left-hand side the optimization history. So now the objective function is like the square distance summed over all powers, and you see that this actually drops from like an order of 10 to the power of minus 5 to 10 to the power of minus 8. And if you look on the figure on the right, so the blue one is the original design, so the CO2 percentages over the powers, and the black one is the optimized design. You see that's an almost perfect fit to the target fuel to air ratio that we wanted to achieve. So that's a quite a nice result, but we had to further had a look at this particular design with respect to what I mentioned at the beginning, pressure drop and mixing quality. So that's maybe also quite interesting. So how does this look like, this optimized design? So the black line is the optimized design, and in blue on the background you see the original design. And what mainly changed is the region right here. You see that there's some curvature where the flow of the gas inlet right here is somehow redirected in the airflow. And this also makes changes to the needle. So that's the one on the bottom. So this also has some curvature. Yeah. Okay, so back to the mixing quality. So on the top, you see the comparison of the methane mass fraction for, in this case, the low mass flow outlet condition, so the low power case, original versus optimized design. And when we look at the mixing quality and measure it based on the scaled sum of deviations from a mean mass fraction measured at the outlet, then we see that actually for all the power cases, this has increased, and in our case, this means that the mixing quality is worsened. So 0 would mean no variation from a mean mass fraction. So that's something we still have to consider in the future. Something we already tackled, and I can present right here, is the problem with the pressure drop. So if you look at the optimized design, and if you look at the pressure contours on the bottom right here, and also the values, you see that the pressure drop has increased for the optimal design, which is something we do not want. But we can easily introduce an additional constraint. It's only necessary in this case for the high power case on the pressure drop, so it shall not be bigger than the original, for the original design. And what we actually achieved is that this even drops at not a high cost in comparison to the original objective function. So that's still 10 to the power of -8 right here. And if we look at the comparison of the two different designs, the blue one is now the new one. You see that there's not a lot of change in the curvature right here, but most of the part is that we have to widen the channel for the air inlet again. So for this particular design, we now did some measurements. So it was 3D printed, and we did measurements on Bosch test lab, did measurements for this 3D printed new design. And the measurements are these dots right here. So for the original blue design and for the optimized black design. And what you see is that actually this is a quite successful result, that we could decrease the distance to this target fuel to air ratio here. So this curve is the better one. But still, if we compare it to our simulation results, the bold lines right here, this is a bit off. So the prediction that we have this almost perfect fit is not valid. So there are still some discrepancies between the simulation and the measurements. And one important factor is, for example, that we just set for the gas inlet 0 back pressure for all the power cases. And that's usually not the case. So this varies, and this is especially for lower powers, we should set different boundary conditions right there. So that's one thing that one can still look at. And also what could be interesting is to include a transition model, so laminar to turbulent transition right here, maybe to resolve better resolve the physics. Okay, so to sum up, we developed the adjoint solution for axisymmetric flows with cold mixing. This was implemented then in an optimization framework, so FADO, involving target objective functions and the multi-point setup. For the application case, we got a very nice improvement, and we could also investigate further on constraints. One point that we are currently looking at is robust design, where we look at manufacturing uncertainties and try to improve the robustness of the design. And another point that I already talked about is the question about mixing quality. Can we further optimize the mixing process, which would then lead to a multi-objective optimization problem. Thank you for your attention.
Thank you. Questions? Yes, there's one in the back.
Thank you so much. It was very interesting. It was also I'm working on at the moment. I was wondering about the use, what's use for example.
I repeat the question for virtual audience. So the question is, what were the parameters in the lookup table?
So the lookup table is the interpolation in the lookup table is the same one that was discussed this morning, I think. So yeah. So it's the interpolation is directly implemented, and we have the progress variable, and then from the lookup table we read like the species dependent properties.
It's another question that Nicolas.
Yeah, I think very interesting. I guess there is you discuss robust design for future work.
Yeah.
You mentioned manufacturing uncertainty, so I guess I was wondering if it's
yeah. So at the moment we are. Oh, sorry, you have to repeat.
The question is about details of robust design.
Yeah.
Will be done.
So at the moment we are looking at. If I go back to the design. Right here. So the idea is that if it's manufactured, this is molded, and if it cools down, it can cool down in different, like depending on the conditions. And then this whole part is shifted, like uniformly shifted in some direction, not shifted, but wider or narrower. And that's what we are modeling currently. And that involves that we have an additional, I'm using just the FFD box definition, and I'm using an additional FFD box for applying these uncertainties. And then then we calculate a mean and a variance from varying this with samples, yeah, and do an optimization on that. Yeah.
Okay, thanks. Further question? Yeah, the next one.
Next one. You showed that the new FFD box with
Yeah.
This is the payment.
No, I haven't. Oh, sorry.
Question about the FFD box model details.
Yeah, so I haven't done like a lot of studies. I just started off with the 15 by 15, and the results were quite nice. I think I also tried a higher resolution, and the results didn't differ that much. So I was confident that it's okay to represent the design. Yeah.
Okay. Okay, let's question from Alberto. I cannot deny a question from you.
No, it's not a question. I had a question like many years ago for a very different problem, which is texturizing. So when we make synthetic carpets, we texturize the thread that goes to the needle, and there is this supersonic flow, and the shear stress creates shear on the thread. The thread becomes like wool. And it's quite an interesting problem because then you have to maximize the shear stress on the symmetry line. And maybe there are some industry that is interested. Yeah, application.
There was a comment about work from Alberto years ago.
No, 20 years ago.
20 years ago.
Yeah, very old. The application, yeah.
Similar application from Lisa.
Yeah. So this would also involve mixing and then shear stresses. Okay.
Yeah, there is no mixing, but
no mixing.
supersonic flow.
Supersonic flow.
You might have constraint with that.
Okay. Yeah. Yeah.
You want to-
Yeah. Interesting.
Thanks to Lisa again.